Hello guys, good morning. Can you hear me all? Okay, so where were we in the last class? What have we discussed? Okay, so last class we have discussed about the factors affecting the rate of the reaction. Okay, and we were talking about temperature, I guess. Yes, yeah. So effect of temperature on the rate of the reaction. Okay, so write down the heading. Write down the heading, temperature dependence of the rate temperature dependence of the rate of a reaction. Okay, so okay, write down this fact. I'll just show you here. Could you see the screen now? Okay, so we were discussing about temperature dependence of the rate of a reaction under factors affecting the rate of a reaction. Okay, temperature dependence. Okay, so write down, temperature has a great influence. temperature has great influence on the reaction rate. On the reaction rate. Okay. The rate of almost all the reaction increases with increase in temperature, increases with increase in temperature, next line. The effect of temperature also depends upon the enthalpy change of the reaction. Enthalpy change of the reaction. Next line. It has been observed that with rise in temperature by 10 degrees Celsius, with rise in temperature by 10 degrees Celsius, the rate constant gets doubled and the ratio of rate constant at two different temperature in bracket you write down at a difference of 10 degrees Celsius. Two different temperature at a difference of 10 degrees Celsius, bracket close, is called temperature coefficient. Is called temperature coefficient. Okay, so what is this term you see? If you take the ratio of K, rate constant, at two different temperature differs by 10 degrees Celsius, K at T plus 10 divided by KT. Okay, this equals to mu. This ratio is mu, and this mu we call it as temperature coefficient. Temperature coefficient. Okay, so this ratio is found to be almost doubled, 2. at every 10-degree rise in temperature. This has been observed. Means if you find out K at 80 degrees Celsius and you find out K at 70 degrees Celsius, so that ratio at 80 by at 70 degrees Celsius, that ratio is found to be 2, almost double of. This is experienced, this is observed experimentally. Okay, the ratio of the rate constant at two different temperatures differs by 10 degrees Celsius is almost 2. In some book it is written 2 or 3, but you should know this information, it is almost double. Okay, now the relation of K, the rate constant and temperature, right, is given by Arrhenius equation. The ratio of rate constant and temperature is given by Arrhenius equation. So you see what is Arrhenius equation? It is given by K is equals to A e to the power minus EA by RT. This is Arrhenius equation. Okay. Where A is the Arrhenius factor, and we also call it as pre-exponential factor. A is Arrhenius factor, or we also call it as pre-exponential factor. EA is the activation energy. Activation energy, T is the temperature. Right? Now, from this relation, Arrhenius equation, we can write down the relation of two different rate constant at different temperature. Okay, let's see how we can do this. Suppose what I'm assuming, K1 is the rate temperature, is rate constant at temperature T1. Suppose I am taking this assumption, and that is K1 is the rate constant at T1 and K2 is the rate constant at T2. Okay. This relation you see in this one, if I take ln both sides, it becomes ln K is equals to ln A minus EA by RT. Okay, if I take ln both sides, we'll get this. Now, at two different temperatures, if I write down the relation with respect to this, we get this as ln K1 is equals to ln A minus EA by RT1, equation 1, and ln K2 is equals to ln A minus EA by RT2, which is equation 2, right? Now when we subtract 2 minus 1, it becomes ln K2 by K1. K2 minus K1, ln K2 minus ln K1 is ln K2 by K1 is equals to minus EA by R 1 by T2 minus 1 by T1. Okay. Further, we can convert this into log. So log of K2 by K1 is equals to minus EA by R, EA by 2.303 R 1 by T2 minus 1 by T1. So both expression you can keep in mind. This is a relation of rate constant and temperature. Done? Finished, guys? Okay. Yeah. So now when you look at this reaction, we know at rate constant, when rate constant increases, rate of the reaction also increases. So if you look at the expression that I have given just now, what we can say, as temperature increases, then rate constant K increases, and hence rate of the reaction increases. You can understand this point. You see the relation we have is log of K2 by K1 is equals to minus EA, activation energy, divided by 2.303 R 1 by T2 minus 1 by T1. So as temperature increases, means what? Suppose I was assuming T2 is greater than T1. This means what? 1 by T2 is less than 1 by T1. This further means 1 by T2 minus 1 by T1 is less than 0. When it is less than 0, it means this term is what? This term is negative. You see, this entire term is negative. So negative, negative becomes positive. Means a log of K2 by K1 is greater than 0. Further, we can say log of K2 by K1 is greater than 0, which means K2 is greater than K1. That is what the point I have written. If temperature increases, K increases, rate of the reaction increases. Okay, you don't have to memorize this. You know the equation, you can do this in the exam also. Okay, relation of temperature in K we have done. Another one is as E increases, as activation energy increases, rate of reaction decreases. Rate of reaction decreases. Okay. You see the second point. This axis, the y-axis, we have potential energy, PE. X-axis, we have the progress of reaction, reaction coordinate. The graph we observe is like this. This kind of graph we observe. Okay. Now you see this here. This point is the energy of reactant. This is the product. And this point, at this point, the maximum energy, the peak that we have, this we call it as activated complex. Activated complex. Correct? This difference in energy here, you see from the reactant to this activated complex, this energy difference is one thing. This energy difference is the another term. We'll discuss this term later on also, right? And this difference here from this to this. Okay. This difference in energy, we call it as activation energy, EA. From reactant to the activated complex is activation energy. This energy is threshold energy, ET, threshold energy. And this difference is the enthalpy change, delta H of the reaction. Okay. The right side we have from product to activated complex is the threshold energy, right? The difference between the energy in reactant and product is the enthalpy change. The difference of the activated complex and the activation energy and the reactant molecule is the activation energy. See, activated complex is a complex molecule which forms during the process of a reaction. Means the reactant molecule, suppose A and B are reacting, correct? So this A and B reaction means they collide with each other, right? And they forms activated complex here. Before converting into the product, they first form activated complex. And if the condition is fine, what condition is there, we'll discuss that. But if the condition is fine, then this activated complex converts into the product. So activated complex has the highest energy, hence it is least stable. You won't get activated complex as the product of any reaction. If activated complex forms, if the condition is there, then that converts into product or it converts back into the reactant. Okay, you won't get activated complex as the product of any reaction. Correct. So that's the one thing. Now, this activation energy, what happens, you see, if this energy difference is less, right, then the reactant molecule easily crosses this barrier and forms a product. But if this energy difference is high, right, it is very difficult for this reactant molecule to reach to this point, that is activated complex, and then convert into the product. So basically, lesser activation energy, easier the formation of product. That's why I have written, and fast the formation also the product is, right? That's why I have written, if EA increases, rate of the reaction decreases. Is lesser value of EA, it can easily cross the barrier and forms a product. Okay, so that's the point of discussion. We have activation energy and activated in this thing, temperature. Okay, why on temperature? Why as temperature increases, rate of the reaction increases? Because what happens for any reaction, the reactant molecule should have minimum amount of energy, right? Should have minimum amount of energy. If that energy is not there, the reactant molecule won't convert into the product. Right? So as temperature increases, the molecules, the fraction of molecules which has more amount of energy, the minimum amount of energy, that fraction of molecules increases. And hence the collision is more, and hence the product is more. That is the reason we have why temperature increases, activation energy increases. So this is the 2 point you have to keep in mind. Right? Have we discussed about this thing? Catalyst, effect of catalyst, have we discussed?
No, sir.
Okay. Yeah, so catalyst effect we have discussed. So this is it, the factors affecting the rate of the reaction we have already done. So temperature one is the most important one out of the 5, 6, whatever we have discussed. Okay. So this is one thing. Now, another thing we have discussed is write down the determination of rates, determination of rate. We are going to see two methods, experimental methods. Heading right down. Experimental method. Two methods we'll see here. The first one is initial rate method. Initial rate method. So what is this method? How do we find out the rate of a reaction by this? Okay. So in this method, write down, we can find out the rate of the reaction. We can find out the rate of the reaction irrespective of the number of reactants molecules involved. Number of reactant molecules involved. Okay. So number of reactant molecule is not any criteria for this. Okay. Whatever reactant molecule is present, we can find out the rate of the reaction. So suppose the reaction is uh, N1A plus N2A plus N2B, N2B plus N3C gives product. Okay. And this rate law is given, rate expression is given. It is K concentration of A to the power X, concentration of B to the power Y, concentration of C to the power Z. Okay, where this X, Y, Z and what? X is the order of the reaction with respect to A. Y is the order of reaction with respect to B, and Z is the order of reaction with respect to C. Okay, now what we do, we'll change the concentration of one of the reactant molecule, keeping the other concentration term constant. Means suppose we'll find out the rate R1, right? R1 suppose is the rate. When you change the concentration of A, only A. Suppose A, I have taken A1, right? And this order won't change because it is the experimental quantity, B to the power Y and C to the power Z. Okay, so you'll have some R1 value over here. Similarly, at other concentration of A, we'll have some other rate. If it is independent of the concentration of A, then there will be no change in the rate of the reaction. But if the rate depends upon the rate of the concentration of A, then with the change in concentration of A, rate also changes, right? Our purpose is to find out the order of the reaction. Okay? So next thing is what? We'll just take the ratio of the two. We'll just take the ratio of 1 by 2, right? So we'll get R1 by R2, and this will be equals to concentration of A1 by A2, A1 by A2 to the power X. Remember, this X is the order of reaction with respect to A, right? Now we can find out this X because we know this R1, R2, A1, A2. So X equals to log of R1 by R2, this divided by log of A1 by A2. This is the value of X, which is the order of the reaction with respect to A. Similarly, we can repeat this method for B and C also. So like that, we find out Y and Z, and overall order of the reaction would be, overall order is equals to X plus Y plus Z, and this is the answer. Clear? Understood? This we call it as initial rate method. Okay, we'll find out the initial rate with respect to one of the reactant, and we'll add the order of each with respect to each reactant species and get the answer. Okay, this is the first method, experimental method. All these are. This one is important. You'll get questions onto this also. Easy questions will get. All the data will be given. Just you need to observe. Next, the second method we have by which we can find out the rate of the reaction, experimental method, is Went Hoff differential method. Went Hoff differential method. In this, what happens, you see, suppose a reaction A gives product. Okay. So the rate expression of this we can write. We do not know the order. the rate we can write K concentration of A to the power n, where n is the order of the reaction, which we can also write it as minus of D concentration of A by dt. This is also rate. So now at two different concentration, we can write down this expression. Okay. So at two different concentration, suppose A1 and A2, concentration A1 and A2, we can write minus of D concentration of A1 by dt is equals to K A1 to the power n. Okay, just we substitute A1. Okay, if you take log both side, it becomes log of minus D concentration of A1 by dt is equals to log K plus n log A1 concentration. Similarly, for concentration A2, we can write log of D concentration of A2 by dt is equals to log K n log A2. Our purpose is to find out n, right? So what we do, we'll just divide 1 minus 2. Anything you can do, 2 minus 1 also you can do, you'll get the same answer. Okay, suppose if you do 1 minus 2. So remember here, this is nothing but, to simplify this, I'll just write down this rate as R1. This minus dA by dt is R1 and minus d2 by dt is R2. Suppose this is R2 here. Okay, so what we can write, you see, we can write log of R1 minus log of R2 is equals to n. What we can write, n log of concentration of A1 minus log of A2. So n is the order, and that is equals to log R1 minus log R2 divided by log A1 minus log A2. Remember, if you have written R1 first, then A1 you should write down here first. If R2 you have written first, then in the denominator R2, A2 minus A1. Right, this we call it as Van 't Hoff differential method, used to find out the order of a reaction, right? Experimental methods, all these are. Copy this. Okay, are you done? Yes, Spurti, any doubt? Okay. Spurti, any doubt? You raise your hand. You can unmute yourself and talk. Okay, I guess no. Okay. Okay. So guys, we have discussed about the rate of the reaction. We have discussed about the order also, right? There is one more term here, which we call it as molecularity. Okay. They have also asked the difference between order and molecularity. Okay, in the board exam, they asked the difference. Mm. Huh. One question you see, it is based on this determination of order of a reaction. You see this question, okay, just one question, simple one only. Uh, a certain gaseous reaction between A and B is given, okay? So this is the gaseous reaction given between A and B. A plus 3B gives AB3, okay? The initial rates are reported as follows, okay? So here we have initial rates given. We have concentration of A, we have concentration of B. Means like I said, we have taken different concentration of A and B, and we observe the rate of the reaction. Okay, so A is nothing but it's 0.1. Then we take 0.2, 0.3, 0.4. Okay, these are the initial concentration of A and B taken. Okay, B is also taken as 0.1, 0.1, 0.2, and 0.3. Okay, and with this data, the rate is observed as 0.002, 0.002, 0.008, 0.018. So again, 0.018. Unit of this is molar per second. This concentration is in molar and this is molar. Find out the rate law. Okay, you need to write down the rate law here. All of you know what is rate law, right? That rate is equals to K concentration of A into to the power something, concentration of B to the power something. That is what you need to write. Done? See, you can write down the rate law as R is equals to Ka to the power X, B to the power Y. Okay. And then you can substitute the value and compare. Are you getting it? Should I solve? Okay, let it be. I'll do this. See, reaction is this. So what we are assuming? We are assuming the rate law as R is equals to K into concentration of A to the power X, concentration of B to the power Y. That is what we need to assume. If you find out this X and Y, so we can find out the rate law also. Okay. And for this, we have the different data given. Okay. First set of data is R value is this data. This is the first set of data. So R value is 0.002 is equals to K. Concentration of A is 0.1, B is 0.1, so 0.1 to the power X plus Y. Or I'll write this as separately only. 0.1 to the power X and 0.1 to the power Y. This is first thing. Now the second data is, you see, concentration of A is doubled and B is same, right? So we can write rate as 0.002 K. Concentration of A is 0.2 to the power X, 0.1 to the power Y. This is 2. Okay. So if you take the ratio of 1 by 2, right? 1 by 2 if you take, so this and this will get cancelled. So we have 0.1 by 0.2 to the power X equals to 1. So 1 by 2 to the power X equals to 1, and that is 1 by 2 to the power 0. So X equals to 0. Did you get it, the first point? All of you, please tell me. Did you get it, how this X equals to 0? Yes or no? Okay. See, this thing you can do, but you can directly say X equals to 0 in this case. Because you see, if you look at the data given, now this one is important, look at the data given here, because when you get this kind of question in the exam, in the competitive exam, you don't have to do all this, right? It takes a lot of time. But in the board exam, right, you can write down like this, steps wise, okay? But in the competitive exam, what we need to do, since A concentration is getting doubled, right? A is getting doubled, there's no change in the rate of the reaction, right? A is getting doubled, but the rate is same. It is not changing. It means what? The rate is independent of the concentration of A. Can we say that? Since when you are doubling the concentration of A, it won't alter the rate of the reaction. It is same we have. It means the rate is independent of the concentration of A. Hence, the order with respect to A is 0, x equals to 0. Can we say that? Yes. Okay. Now for B, what we have to do, we have to take the other set of data. Suppose I am taking the third one, third data I am taking, I'll write down here only. Third data I am taking. Okay. So we can write rate equals to third one, this one, 0.008 equals to K into 0.3 to the power 0 because x is 0 and 0.2 to the power y. Okay, so this is 3. Now if you divide 1 by 3, 1 by 3, so what we get, 1 is this 0.002 by 0.008, left hand side we have 4 equals to K, and this will get cancelled, 0.1 by 0.2 to the power y. So when you solve this, you'll get y is equals to 2. Y is equals to 2. And hence, the order with respect to B is 2. So the rate law for this particular data, for this particular equation, we can write K A to the power 0 and B to the power 2. This is the answer for this question. All of you, did you get it? No doubt. Okay, so just you need to assume the rate law, and then by substituting the value, you should find out the x and y.
Ramesh, there is no feedback.
What? Hello? Any doubt? Okay. Now, one more thing you can observe, like I said, that all these steps you should use, but how we can do this directly, this question that you see, when this rate of B becomes double, right, becomes double, so this becomes what? This becomes 4 times. And that is only possible when the power of this is 2. Hence the order is 2. You can say it directly, no? When the rate concentration of B becomes double, the rate becomes 4 times. So that is only possible when the power of the concentration is 2, and hence the answer is 2 with respect to B. Clear? That is how we can do this question directly. But like I said, in the board exam, you have to write down the steps, equations, and then take the ratio. But competitive exam, you don't have to write down all these steps. Just you observe the data, take the ratio, and you can understand this. Y is equals to 2, then the answer will not be equal to 4. Tell me what happened here. If you put y is equals to 2, no, this is a method we are using, Pranav. You see this. When concentration becomes double, right, rate becomes 4 times. Rate becomes 4 times. So that is only possible when the power of concentration is 2. Then only twice increase in concentration will increase the rate by 4 times. What should be 1 by 4? Acha, here you are talking about. Acha, here it is 1 by 4. It is, I have written it by mistake. Yeah. This is 1 by 4, correct. Because we have taken 1 by 3, no? So this is 1 by 4, right? By mistake. Okay. So this is method we can use, but from here also you can do it directly. You don't have to do it, right? Twice square and then 4. Okay, fine. Okay. Yeah. So the next term we have to understand here is molecularity. Molecularity and order, it's very important, right, for your board exam. They ask this question in the exam, what is the difference between the order and molecularity? So write down, we have 3-4 difference here. Write down. It is equals to molecularity, write down definition. It is equal to the sum of the reactant molecules involved in sum of the reactant molecules involved in the balanced stoichiometric equation some of the reactant molecules involved in the balanced chemical equation, chemical equation. Okay, again I am repeating. It is equal to the sum of the number of reactant molecules present in the balanced chemical equation. Next line. In case of a complex reaction, what is a complex reaction? Anyone? What is a complex reaction? In which we have more than one steps, okay, non-elementary, okay. So when we have more than one steps in a reaction, which means in case of a complex reaction, the molecularity is defined as the number of reactant species. Molecularity is defined as the number of reactant species involved in the rate determining step, which is the slowest step of the reaction. Write down involved in the rate determining step In the bracket, you write down the slowest step. Okay. You see this example, if you have taken dissociation of PCl5, PCl5 converts into PCl3 and Cl2, and it is a single step reaction, simple reaction. Since only one molecule is involved, we call it as unimolecular. Unimolecular reaction. If you take a dissociation of HI, 2HI gives H2 plus I2, two molecules involved, so it is bimolecular. All these are single step, guys. Bimolecular reaction. If it is 2SO2 plus O2 gives 2SO3. So the number of the molecules involved is 3. So it is trimolecular reaction. Okay, these three different types of reaction we have based on the molecularity of the reaction. Correct? The next one is the decomposition of H2O2, you see. Of H2O2, it is a two-step reaction, complex reaction, two-step reaction. Like you see how this reaction goes. H2O2 first converts into H2O and half O2. This is the first step of the reaction. Okay. So sorry, this is the overall. I'll write down this as this one. Just a second. We have nascent oxygen here. First step of the reaction. Now in the next step, what happens? This H2O2 and this nascent oxygen again combines and forms O2 plus H2O. O2 plus H2O. So with these two reaction, we get the overall reaction. Overall reaction, we can write down in one single step, and that is when we add the two reactions. So H2O2 gives 2H2O. Right, so it is 2H2O2 gives 2H2O and O2. This is the overall reaction. But this reaction we get from this two reaction. So it involves two steps. This one is the slowest step. Slowest step, RDS of the reaction, rate determining step. This one is fast. With fast step, we cannot define the rate. Okay. Now in this step, you see in this reaction, since there is only one H2O molecule, H2O2 molecule here, in the slowest step, we have only one H2O2 molecule. It means this reaction is what? This reaction is a unimolecular, or the molecularity for this reaction is 1. Is 1 for this. Okay. So by looking at the reaction, you cannot say. If you look at this reaction, the overall reaction, it is coming out to be 2, right? But that we cannot say because the reaction is not simple. Okay, it is a complex reaction. It is experimental actually. You should have this idea that which one is, simple reaction, which one is complex reaction. Once you have this idea, you can talk about all this. Okay, but few examples you must remember. Like few examples I have given you. You must remember all these are simple reaction. You must know this. Okay. The another one is there are 2-3 points here in molecularity which is important. Write down. It is a theoretical concept. Point wise, write down. It is a theoretical concept. Theoretical concept. Next point. Cannot be zero. Negative. Cannot be zero. Negative. Fractional, etc. Okay. So if you see the difference between molecularity and order you remember, I have told you that it is a experimental quantity. Order is an experimental quantity, but molecularity is what? Molecularity is theoretical concept. It is not experimental. First difference. Second difference, order can be zero, can be negative, can be fraction, anything possible for order, right? But molecularity cannot be zero, right? Because it is nothing but the number of reacting molecules, right, in the slowest step. So that cannot be zero, negative, or fraction. Okay, so this is the difference between molecularity and order. Understood? Okay. Now, two more things we have to discuss. One is the reaction mechanism. One is the reaction mechanism, and other one is the collision theory of reaction. Okay, theory behind the reaction. What all theory is there? Okay, so H2 I2. You see the second reaction I have given you. 2HI gives H2 and I2. Okay, this reaction is bimolecular reaction, right? Since two molecules are involved into this. But again, I'm telling you, PCl5 is unimolecular and it is simple reaction. H2I, sorry, HI that forms from H2 and I2, that is not a simple reaction, but their molecularity is 2, bimolecular. SO2 plus O2 gives SO3, right? Their molecularity is 3 because 3 atoms or molecules are involved into this. Okay, so this point, this particular thing is little bit experimental. By looking at the reaction, we cannot say whether the reaction is single step or multi-step reaction. Okay, so when you see some questions, you'll understand this. Okay, so next thing we'll discuss the reaction mechanism. What is a reaction mechanism, and what all things, what all concepts we can get from the graph of any reaction that we are going to study here. So they ask this graphical question also in the exam. Okay, and it's very simple. You just have to understand it. Okay, it's not that complex concept. You can understand it easily and you can easily gain marks into this. It's very easy. Reaction mechanism. What is reaction mechanism? Write down. It is the step-by-step description it is the step-by-step description of a chemical reaction step-by-step description of of this chemical reaction. Next line, each steps are based on the observed rate of the reaction. Observed rate of the reaction. So again, you see, all these are again experimental. The number of steps that we have and their observed rate. If the rate is very high, with respect to that only we can say which step is the rate determining step. Okay, rate determining step of any reaction is the slowest step always. Okay, so for example, you see 1, 2, 3 examples we'll discuss over here. Suppose I'm taking a reaction and it is a complex reaction, and the reaction is H2 plus I2 gives 2HI. This reaction is overall. Even the reaction of H2 plus Br2 also is a complex reaction. Right? H2 plus Br2 is a complex reaction. Okay. Now, how this reaction takes place? You see the various steps involved in this reaction. Step one is, first of all, this I2 converts into 2I, iodine atom. Okay, and it is reversible, both way it can go. Okay, then the hydrogen in step 2, what happens? The hydrogen H2 combines with this iodine, which forms in the first step, and converts into H2I, right? Step 3, this H2I combines with the another iodine atom, and this converts into 2HI. Okay, so these are the steps involved. Now, when you add all these 3 steps, right, you'll get the overall reaction. And when you add this, you see H2I gets cancelled, right? I gets cancelled. Okay, so overall order is what you see. The overall order is, the overall reaction is H2 plus I2 gives 2HI of the reaction. But in these 3 steps, like I said, we have to consider only the slowest step, the rate determining step. So this step is fast. The first one is fast. This is also fast. And the third step is the slow step we have. So this step is the RDS of the reaction, rate determining step. And we'll find out the molecularity with the number of species involved in reactant species involved in the rate determining step, which is 2, H2I and I. Hence, molecularity of this reaction is 2. Did you understand this? Finished? Can I go to the next page? Now, one more thing I would like to add over here, that if you write down the rate of this reaction, okay, rate expression, rate law, that will be K into the concentration of the species involved in the slowest step. That is the rate determining step. Okay, so that would be what? That would be H2I and I. This is what the expression we write. Okay, H2I and I, because H2I and I are the reactant species involved in the rate determining step. One more thing, it's very important here, is in this rate law, we cannot write, in this rate law, we cannot write any intermediate product. You see, I is an intermediate product. H2I is an intermediate product. Okay, intermediate molecule actually. Overall, what is happening? H2 plus I2 gives 2HI. So this is reactant, this is product. Okay, intermediate molecule we should not write in the rate expression. Write on this point here. Intermediate molecule should not be written in the rate expression. Okay, should not be written in the rate expression. So we have to actually replace this H2I in terms of H2 and I2. We have only the reactant molecule in the rate expression. You see, this reaction is what? This reaction is reversible in nature. So suppose this is rate constant is K1 and this is K2, equilibrium constant, K1 and K2. So K2 we can write, you see here, K2 we can write concentration of H2I divided by the concentration of H2 into I, right? We can also write K1 from this. K1 is equals to I square by I2. Okay. So what is I from this? We can write K1 into I2 is equals to I root under of it. Now when you substitute this here, we'll get H2I is equals to H2 into K2 into I is K1 I2 root under of it. Okay. Basically what we are doing, we are replacing all the intermediate atom molecule in terms of the reactant molecule H2I2. Okay, we are replacing that. So for that we are using the expression of equilibrium constant K. Any doubt? Yes, tell me. So what we get here, you see, we can write this K. H2I is what? H2I is, we have K2 into root over of K1 into I2. H2I is this, K1 into I2. And see, H2I concentration is what? H2 K2 into K1 into I2 root over. So K2 I2 into H2 we should write. So this is the concentration of H2I. I is what? I is root over of K1 into I2. Now when you solve this, what you get, you see here. I'll write down this side, wait. This side, you see. We get K into K1 is K1, root over of K1, K1, K2 we have as it is, into root I2 into root I2 is I2 into H2. So this is the product of the equation of Hello, can you hear me, guys? Yeah, can you hear me?
Yes, sir.
Yeah, there was a technical issue. Anyways, so fine. So did you understand this? So what I have done, quickly I'll tell you, we have just replaced all the intermediates, atoms or molecules in terms of the original reactant molecules that we had. we have. Okay, by using the equilibrium relation. Okay, so we have, you see here, I have replaced this because in this suppose we have to start with this slowest rate h2i into I, but if you see both h2i and I are the intermediate molecules in atom. The reactant molecule is H2 and I2. So in the rate law expression, we must have H2 and I2 present. Okay, so what we do, we have to replace this H2I and I in terms of H2 and I2. So for that, we use we take the help of these two steps. So you see, for this one, we can write the equilibrium constant K2 as concentration of H2I divided by H2 into I. That's what I have written here. Okay, this is one thing. For this one, we can write I by I2, I squared by I2, which is this. So we'll find out I in terms of I2 from this. So I is equals to K1 into I2 root over of it. This I, if you substitute here, you will get H2I in terms of I2 again, H2 and I2. Now this H2I and I will substitute it over here and we'll get this expression. So the rate expression we get, if I write down this, the rate R is equals to, we get K into K1 into K2, concentration of H2 into concentration of I2. So you can say these are the constant. So we can write this constant collectively as suppose K dash into H2 and I2. That's how the rate expression we write for this. Okay. So for this reaction, H2 plus I2 gives H2HI will have this kind of relation. So whenever you have multi-step, you write down the rate expression with the help of the slowest step of the reaction. If any intermediate molecules or atoms are present in the rate law, we have to convert that into the original reactant molecule. So for that, we use the other steps which is involved in the reaction. One more we'll see on this. You try to write down the rate expression of this one. Number 2. You see, the reaction is NO plus Br2, 2NO plus Br2, and this gives 2NOBr. This is the reaction. Okay. The steps involved into this, I'll write down the steps here. I'll write down the steps here. Hello. Rajir, I'm in class. I'll call you after 11, okay? So first step is NO plus Br2. It gives NOBr2. This information I'm giving you. Even in the question also, this steps will be given because we cannot memorize all these steps. The second step is what? The second step is NOBr2 plus NO. This gives 2NO. This is the slow step of the reaction. Okay. So suppose this is K1, this is K2. Now you find out the rate expression for this reaction. Rate expression for this reaction. Find out it. Done. Okay. You see this? The rate expression, like I said, we always write with the first, the slowest step. So rate is equals to, we can write some rate constant K into the concentration of NOBr2 into NO. Now this NOBr2 and NO, both you see, NO is the reactant molecule, but this NOBr2 is what? It is the reactant, it is the intermediate molecule. Okay, okay. This is the intermediate molecule. This NOBr2 we have to convert in the other reactant species. So for that, what we can use? We can use the relation of this. So K2 we can write, you see, K2 we can write NOBr square divided by NOBr2 into NO. So we can find out NOBr2 from this, right, in terms of NO. So NOBr2 in terms of NO is what? It is NOBr square divided by K2 into NO, first thing. Okay. This NOBr2, now we have got in this term NOBr, which we can further write, because you see NOBr is here, which we can further write K1 is equals to concentration of NOBr divided by NO into Br2. So this NOBr2 we can replace as NOBr as K1 into this. So here you see concentration of NOBr, or I'll just substitute into this one. You'll get a simple expression. K. NOBr2 is what? We'll write down NOBr square divided by K2 into NO. So this NO and this NO would get cancelled. And then NOBr square we can substitute as K1 into NOBr2 whole square. So that will be K by K2 will be as it is into K1. You don't have to worry about this K thing, right? K1, K2, K, whatever you're getting. You don't have to worry about it. Okay, because we can write all these things as a constant, right? So this further becomes what? K into K1 square by K2 NO square Br square is the expression. This becomes a constant term, that is K, and this square into this square. This is the expression we get. Oh, just a second, guys. Uh, I think this should be NOBR2 here. I missed this 2. Then only this will react with this here. We'll get this. So I think I have to change this thing here. This is NOBR2. Just a second, guys. I'll do this again. Um, One quick thing. This is fine. The first expression is fine. K2, well, I will see. This expression will write down again because this should be NOBR2. Otherwise, in this reaction, I have written NOBR2. From where this NOBR2 will get? It will get from the first expression, right? From the first expression, you see that the rate expression is this NOBR2 we have to replace. So NOBR2 from the first equation we can write is K1 into NO into BR2. Now this is fine. That's what I thought. Both term square we do not get. This will substitute simply over here, and this will be a simple expression K into K1 into NO square BR2. That's what I thought. To the third order reaction, we were getting 4 over there. So it is K into K1, we can write on a constant, that is K dash, suppose, into NO square into BR2. That is it. Okay, I missed this too. This should be here because the intermediate that you get in the first step, that will only react in the second step. So it should be same here. So like this, we can find out the expression of K, okay, NO square into BR2. There's one very important, example we have for this, and I want you to do this. That is the depletion of ozone layer. The rate law expression they have asked many times for this ozone layer. Okay, so the reaction overall, you see, it is 2O3 converts into 3O2. This is the overall reaction we have. What all steps involved? Step one is O3 converts into O2 plus we get nascent oxygen. Okay, this is the fast reaction. First step. Step two is O3 further combines with this nascent oxygen and we get 2O2. This reaction is slow. Okay, this is suppose we have K dash and this is suppose we have K1. Find out the rate law expression for this. You will get this question in a textbook also. If you solve the multiple choice question, it is there. Are you done? See, in this one, what we do, first of all, with the slowest rate, simple thing is what? With the slowest rate, we write down the rate expression is gas into concentration of O3 and O. Okay, concentration of O3 and O. This O is the intermediate, so we have to replace this. How do we replace this? By this K1 expression. K1 is what? O2 into O divided by O3. So what is O from this? Concentration of O is K1 into O3 by O2. So when you substitute this here, this becomes K dash O3 and O is O3 by O2 into K1. So K1 into K dash, I'll take it as a constant K. Expression becomes O3 square and O2 to the power minus 1. Right, O3 square, O2 to the power minus 1. The overall order of the reaction is 2 plus minus 1, that is 1. Okay, overall order is what? The sum of the power 2 plus minus 1, that is 1. Done? Did you understand this? Please reply. Okay. Now you see the energy profile of a multi-step reaction. Write down energy profile of reactions. I'll write down. See here what happens. The reaction could be endothermic or exothermic, right? Okay, see this axis. This is the energy axis we have, y-axis, and this is the energy axis. You will get this graph-based question also you get in the exam. Okay, simple one. And this is the progress of reaction, progress. This is also reaction, progress. Okay. Now, two types of energy profile we have. I am just talking about here the single step reaction, right? And then we'll see what happens in multi-step. So whatever reaction we have, the pattern of graph goes like this. Just a second. Goes like this. Either this or this, right? This is the energy of reactant and this is the energy of product. Energy of reactant and energy of product. Okay, so you see in this reaction, the difference between the two here, you see the difference between the energy of reactant and product, which is this, right? And here we have this difference between energy and product. So this difference is the enthalpy of reaction, that is delta H. Enthalpy of reaction, delta H. So could you tell me in the first one, delta H value is negative or positive? The first one, delta H value is negative or positive? Yes, guys. Delta H value negative or positive in the first one. Delta H value is what? We are going from high energy to low energy. Means this much amount of energy is getting released. So it is delta H is what? Delta H is less than 0 here. Because product minus reactant less than 0. Here delta H is greater than 0. Right? So this reaction is, like I said, this is at high energy, this is at low energy. So this much of energy has been released. So it is exothermic. It is a graph of exothermic reaction. And this much of energy is getting consumed to reach this higher energy level. So this is a graph of endothermic reaction. And we know delta H for endo and exothermic reaction. Clear? Now, this is what we have. We have one reactant, activated complex, and then product. Right? One reactant, activated complex, and product. Reactant, activated complex, and product. Right? When we have only one step, single step. Right? So in single step, we have one peak and a product, one peak and a product, right? But if you have multi-step reaction, so in multi-step, the graph could be like this, goes this way, depending upon the number of steps involved. Okay, depending upon the number of steps involved and the energy involved in each step. Okay, so I'm just giving one example here and I'll make you understand this thing. So suppose I draw a graph, which is this, and this graph is for a multi-step reaction. Randomly, I'm drawing a graph and we'll try to conclude 2-3 points from this. Okay, you can get any such graph in the exam and they'll ask you all these questions which we are going to discuss over here, right? So graph could be like this. Suppose we are starting from this point, go like this, come down, right? Then it will go like this, come down, go like this, come down, and go like this. Okay, just a second, change it. Okay, this is energy profile and this is progress of reaction. Now you see, first of all, what all things we can conclude from this graph. Suppose this random graph is given for any multi-step reaction. So first thing first is what? That this is what? Reactant or product. This is reactant and the energy of the reactant is this. This is the product and the energy of the product is this. So could you tell me the energy of the product is more than the energy of the reactant? Yes? Could you please respond? The energy of product is more than the energy of the reactant. Yes? Okay. So what we can write, the first thing we can conclude here is the energy of product is more than the energy of reactant. Hence, the reaction is overall, the reaction is endothermic. Delta H greater than 0. This is the first thing we can conclude. If this graph comes over here down below the energy of this reactant molecule, then overall it is exothermic. Right? It is not like overall the reaction is endothermic. So each step will be endothermic. That is not like correct. The intermediate steps can be anything. It can be exo or endo. But by looking at the energy of reactant and product, we can say the overall it is endothermic. Means overall the energy is getting consumed. Right? Now you see this thing here. From this reactant, we'll go to the peak threshold energy, maximum energy activated complex. And this point, you'll get the first transition state. It is TS1, which is an intermediate. It is not the product. Then this is the second step, and this is TS2, second transition state. This is third transition state, TS3, and then we'll get the product. So if you see here, this thing, okay, this thing from this reactant to this transition state, this thing is the step 1. From this transition state to this transition state, this is a step 2. Step 2. Now from here to here, this is a step 3. Right? And then from this point to this product, this is step 4. Right? So I'll write down all these things here. First of all, if they ask you the number of steps involved, so the number of step is 1, then 2, then we have 3, step 3, and this is step 4. So one question that they ask, that how many steps involved in this reaction, the graph that is given. So number of steps is equals to 4. The number of steps, we can also say the number of peak that we are getting, 1, 2, 3, 4. The number of peak is 4, hence number of steps is also 4. Just you peak, you count, that would be the number of steps. Okay. Number of transition state, how many transition state we get? All these are questions. It is equals to the number of steps minus 1. That is what we get, number of transition state. You see, we are getting 3 transition state. Okay. Overall, I said the energy is endothermic, the steps is endothermic. You see, if I talk about step 1 is endothermic because the energy of the transition state is more than the energy of the reactant molecule. So step 1 is endo. Step 2, you see, step 2 is exo. Are you getting it? Please reply. Step 3 is again endo. And step 4 is exo. Is it clear? Now, the last thing here that you should know is the rate of the reaction. Means which step is the fastest step? Which step is the fastest step? And which one is the slowest step? That is what you should know. There are 4 steps involved. Which one is fastest and which one is slowest? So fastest step is the one which has minimum activation energy, minimum EA activation energy. Slowest step is for maximum activation energy. Right, so minimum activation energy, you see, the activation energy is nothing but this difference, this energy gap. from the reactant to this peak. Okay, so this is the activation. Here the activation energy is this. Here the activation energy is this. And here the activation energy is this. Right? So all these gaps are activation energy. Like this difference is the activation energy. Means it is EA1, suppose for the first step. This is EA2 for the second step. EA3, third step. And this is EA4 for the fourth step. So you can see this energy gap is minimum, means what? The fourth step is the fastest step, and the one which has the maximum is the step 1. So step 1 is the slowest step, and this is the RDS of the reaction. So they can ask you this question given, they'll give the graph like this, and they can ask you which step is the RDS of the reaction. So you have to choose the step which has the maximum EA, activation energy. Okay, overall the product, the energy of the reaction is, the energy is getting consumed because the energy of product is more than that of reactant. You can get any possibility into this one. And this graph could be over here, and this could be like this, going up only like this, it can be like this, anything is possible, right? But overall, I have given you the idea of this graph, what all things we can conclude from this graph. They have asked questions on the number of steps involved, number of transition state. This is not that important, and the fastest and slowest step they have asked. Did you understand this? Okay, guys, so we are left only one topic in this chapter, that is the collision theory of reaction basically. So after this chapter, what chapter we need to start? Could you tell me? Yes. What is the next chapter we have to start? I'm not getting any reply. Please tell me. Alkyl aryl halide. Solid state. Okay, fine. I got only one response. Okay, that is for solid state. We'll start solid state next. Okay, we'll finish this in the next class, and then we'll start solid state. Okay, guys, thank you. Bye.
Thank you,
Thank
sir.
you. Thank you, sir.